Detection of negative weight cycle in Bellman Ford and Floyd Warshall. The purpose of this lecture is to understand what is the difference between the logic that we use in Bellman Ford to detect negative weight cycle and in Floyd Warshall algorithm to detect negative weight cycle. In both cases, both of these are graph algorithms which are useful for finding the shortest paths. But while we are detecting negative weight cycle, the logic that we are using, it is different in both of these. This is what we are going to compare here. Okay. First, let us take Bellman Ford. In case of Bellman Ford algorithm, this is a single source shortest path algorithm, meaning from a single source vertex, we'll find shortest path to all other vertices that are present in this graph. Okay. We'll take one example graph here. Let this be the graph that we have. If this is the graph, I'll name the vertices A, B, C, D, E. These are the vertices. Okay. In case of this graph, how will you apply Bellman Ford algorithm? You have to relax all the edges V minus 1 times. What is V here? V is the number of vertices. Okay. In this case, you have 5 vertices, which means you have to relax all the edges 4 times. How are you going to do this relaxation? In the first round of relaxation, you will relax all edges AB, AC, BDs, so on. All the edges once. Again, in the second round of relaxation, all the edges will be relaxed once. Third round, again same, like total 4 rounds. When you relax it 4 times, you know you would have found the shortest path from the source vertex to all vertices. This logic we already discussed in case of Bellman Ford. Now the question is, how are you going to detect negative weight cycles? If you have a negative weight cycle, how are you going to detect this cycle? For this, the logic used here is, after V minus 1th iteration, we'll do one more iteration, the Vth iteration of relaxing all the edges. While you relax for the Vth time, in case you are able to find any improvement in the shortest path, that is, if any of the paths changes, if it was, let us say, previously of length 4, in the Vth relaxation you found it to be a new path of length 3, then in this case, in case any of the paths changes in the Vth relaxation, that means there is a negative weight cycle present in this graph. How are we saying this? What is the logic behind? The logic behind is, when you relax each edge, we are seeing all the possible shortest paths which are using one edge, that is distance of 1. All the shortest paths which are available, if you calculate only distance of one edge, those are the ones you are finding out after the relaxation of first iteration, that is relaxation of one edge one time. After that, when you do second iteration, that is relaxation of all edges for the second time, you are finding all the possible shortest paths which are using at max 2 edges. When you do for the third time, you are finding all the shortest paths which use at max 3 edges. And the final iteration, V minus 1th iteration, what are you finding? You are finding all the possible shortest paths from the source vertex which are using at max V minus 1 edges. This is why you have to be careful. There is a property that if you are having V edges, then the shortest path will have at max V minus, if you have V vertices, then the shortest path from any point to any other point will have at max V minus 1 edges. What is the reason? If you are having a total of V vertices, let us say these are the vertices, I'll have 3 vertices here. If I have more than V minus 1 edges, that would automatically mean there is a cycle. What is the reason? Let us say I draw one edge here, another edge here. That means I already connected all the V vertices. If I have V minus 1 edges, that is good enough to connect V vertices. After connecting all the vertices, that is like a chain, if I add one more edge, I'm 100% sure that I'll be introducing a cycle. Even if you take 4 edges, let us take 4 edges or 5 edges and understand this. If I'm, let's say, drawing v minus 1 edges, I have 5 vertices here. I am going to draw v minus 1 edges, that is 4 edges. Let the first edge be here, 1, 2, then I'll draw third, one more will become 4. Okay, if I do this again, now I have 4 edges and 5 vertices, that is v minus 1 edges are present, and the complete graph is connected now. If I add one more vertex anywhere, let us say I add here, that would mean it forms a cycle. That is why if I know already the graph is connected after v minus 1 iterations, if there is any change at the vth iteration, that would mean it will form a cycle. If it forms a cycle, now the point is, how am I saying that there is a negative weight cycle in the graph? Okay, it's not just about cycle. If you know that there is a cycle in the path, now think back. When will you have a cycle in the shortest path? Here we are finding the shortest path from one point to another. When you are finding shortest path from one point to another, when will you have a cycle? Think about this. Let us say I am finding shortest path from this point. This is A to this point B. If I want to go from A to B, ideally I can go like this. 1, 2, 1, 2, 3. 3 steps I will reach B. Let us say the weight of all these are 1. Weight of all these edges are 1. I can actually reach like this. From here, here, here. I'll reach B. But if I'm taking this cycle, I'm coming here, then here, then here, 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 like this. If I'm taking the cycle and then going to B, what does that mean? If I'm taking the cycle and still getting the shortest path, that means this cycle is doing something to decrease the length of my path. Let us say if I go like this, I'll just name all the vertices so that A, B, C, D, E. If I go A, C, D, B, if I take this path, total length is 3. When will I take the cycle A, C, D, E? If I take this cycle 2 times and after that I go from A, C, D, B, then what does that mean? That means, that is while finding the shortest path. That means the cycle is helping me in order to decrease the length from 3. When can a cycle help me in order to decrease the length that is already existing? Here if I go through this cycle, it is going to be 1, 2, 3, 4. 4 will be additionally added if I traverse through the cycle. But now think back. What if this value is minus 1, this value is minus 1, this value is also minus 1. If those 3 values were minus 1, then A, C, D, B will give you 1 plus minus 1 plus 1, which is a total of 1. But if I decide that I'll take the cycle which is A, C, D, E, A and then again continue with this ACDB path, what happens now is this ACDEA cycle, this will give me 1 plus minus 1 plus minus 1 plus minus 1, that is minus 2 as the total length of this cycle. Adding this cycle will make it minus 2 and then if I take this path, it will be minus 2 plus 1, which is 1. Minus 1. So instead of the actual minus 1, I got final value as minus 1 if I took this cycle. When did this happen? This happened because the cycle is a negative weight cycle. Now if I keep doing this, if I keep taking this cycle again and again and again, my shortest path length is going to decrease and decrease and decrease. This will keep on decreasing. That is why you will never be able to find the shortest path if a negative weight cycle is present. So here Bellman Ford is using this logic in order to detect negative weight cycle. Okay. Now let us see the case of Floyd Warshall. What is the difference in the logic used by Floyd Warshall? That is what we want to see. What we already learned, that is Bellman Ford. In case of Floyd Warshall, what is the difference in logic used for finding negative weight cycle? First of all, keep in mind, Floyd Warshall is not a single source shortest path algorithm. It is a all pair shortest path algorithm. That is, you will find the shortest path between all the pairs of vertices that are available. Okay. When you're doing this, In order to detect the negative weight cycle, what Floyd Warshall does is, once it completes the whole algorithm, that is, the algorithm is, you will consider each vertex k as an intermediate vertex, and then considering this for each case of k, you will find all the possible pairs of vertices uv, and for all these vertices, you will see whether using this intermediate vertex to pass through will help you in decreasing the total distance. If it decreases, then you will update the distance. This is what you are doing in Floyd Warshall. So you will do this for all the intermediate vertices, and then finally you will find the final answer, which is a distance matrix. Next question is, how are you going to find the negative weight cycle and what is the logic used? So here we are comparing the logics in both these algorithms. The logic used here is, if after completing your Floyd Warshall algorithm, in case of Bellman Ford, you did an extra iteration. Here you won't do any extra iteration. Instead, as you complete the Floyd Warshall algorithm, if your distance matrix is having any of the diagonal entries as negative value, that is, any of the entry dii, if any of these is having a negative value, if it is less than 0, that means there is a negative weight cycle present in this graph. Now let's get into what is the logic of this statement. Under what logic am I saying that there is a negative weight cycle if any of the diagonal elements are lesser than 0? First of all, what does any diagonal element in this distance matrix denote in case of Floyd Warshall? Diagonal matrix is distance from the vertex I to vertex I, which means you are standing in some vertex, you are finding distance to the same vertex. This we know is anyway 0. Common sense, this is always 0 because you are not taking any edge, you are simply standing at a vertex. Let us take a graph similar to what we considered previously in case of Floyd Warshall. In case of Bellman Ford. If this is the graph, let us say you are standing at this vertex A, then dii is distance from A to A, which is 0. Now think, when will this become negative? This will become negative only if this vertex A is part of a negative weight cycle. The reason is, just think about this. If I have this vertex A here, and if there is a cycle available here, think of this is a cycle and this is a negative weight cycle, okay? A, B, C, this is having -1, -1, -1. So if you just traverse through this cycle, you will get value -3. This is when distance from that vertex to itself has gone negative. When will this happen? When the vertex is part of a negative weight cycle. In no other case it is possible. Let us say vertex is part of a negative weight edge. That is, if this edge is negative, -2, it is going from here to here. But distance from A to A will not be negative. If that has to be negative, A should be part of a negative weight cycle. And one more thing, let us say A is here, and a negative weight cycle is reachable from A. Let us say this is a negative weight cycle. It is reachable from A. Here it is not necessary that dii will be less than 0. It may be less than 0, it may not be less than 0. But if there is a negative weight cycle in the graph, at least one vertex of that graph has to be part of the negative weight cycle. This is for sure. That is, if your graph has a negative weight cycle, there should be at least one vertex in the graph which is part of the cycle, not just reachable from that vertex. That at least one vertex will be there which is part of this cycle. For that vertex, surely the distance from that vertex to itself will be lesser than 0 in the final output of distance matrix of Floyd Warshall algorithm. This is the logic that we use in Floyd Warshall algorithm in order to detect negative weight cycle. So this I just wanted to give you clarity on the difference in logic that we are using in order to identify negative weight cycle in Bellman Ford algorithm versus what are we doing in Floyd Warshall algorithm.